This study is on efficiently answering probabilistic threshold top K queries on uncertain data. I'm Ming Hua, a PhD student from Simon Fraser University. This is a joint work with Professor Jian Pei, Wenjie Zhang, and Professor Xueming Lin. The related papers are published in ICDE 2008 and SIGMOD 2008. To motivate our study, let's look at the sensor network monitoring the duration of panda presence. In some locations where pandas are more active, multiple sensors are deployed to improve the detection quality, such as sensors S2 and S3, and sensors S5 and S6. Unfortunately, the data collected in sensor networks is often imprecise due to the limitation of equipment and delay or loss in data transfer. An uncertain table is used to store the collected data. Each record is associated with a confidence value, which means the record takes a probability to appear in the table. The two sensors in the same location may detect the presence of panda at a similar time, such as R2 and R3. However, the reported duration values are inconsistent, so only one of the records can be true. This exclusive relationship is captured by a generation rule on R2 and R3. The same situation happens to R5 and R6. The uncertain table can be viewed as a summary of a set of possible worlds. A possible world is a possible snapshot of records that can be observed. For example, a possible world W1 contains R1, R2, R4, and R5. So the probability of W1 is a product of the confidence of those tuples. The set of possible worlds are governed by generation rules. For example, R2 and R3 are exclusive, so they never appear together in one possible world. Among those records, a scientist might be interested in the records with the top two longest durations. Therefore, the top two records on duration in each possible world are computed. For example, R1 is ranked top 2 in W1 to W6. So the sum of the probability of those possible worlds is the probability that R1 is ranked top 2 among all tuples. This is called the top 2 probability of R1. It is interesting to find the tuples whose top 2 probability is high. So we proposed the probabilistic threshold top K queries. Formally, given uncertain table T and a ranking query Q, a probabilistic threshold top K query returns the set of tuples where each takes a probability of at least P to be in the top K lists in possible worlds. For example, in the uncertain table about panda presence, if we set K to 2 and set P to 0.35, then R2, R3, and R5 are returned. We also proposed efficient query answering methods. First, the dominant set property tells that for a tuple T, its top K probability only depends on the tuples ranked higher than T. Based on this property, we process the tuples in the ranking order. We first consider the basic case without generation rules. Then our method is extended so that rules can be handled. In the basic case without generation rules, all tuples are independent. To compute the probability of Ti plus 1 being ranked at the J plus 1's position, we only need to think about all tuples ranked higher than Ti plus 1, which is called the dominant set STI. Then, Ti plus 1 is ranked at the J plus 1's position if and only if Ti plus 1 itself appears. And at the same time, there are only J tuples appear in STI. Now the problem becomes how to compute the probability that J tuples appear in STI. The probability that J tuples appear in STI can be computed iteratively. We consider the following two cases. First, if Ti appears, then there must be exactly J-1 tuples appear in STI-1. Second, if Ti does not appear, then exactly J tuples must appear in STI-1. Combining the two cases, we get the following formula. When generation rules are involved, two challenges arise. First, the tuples in the same rule are no longer independent. For example, whether R2 appears or not will affect the appearance probability of R3. Therefore, the formula in the basic case cannot be used. Second, the probability that j tuples appear in STI cannot be computed from STI-1 anymore, because some tuples in STI-1 may be missing in STI. For example, R2 appears in the dominant set of R5, but does not appear in the dominant set of R3. Therefore, we have to compute the probability for SR3 from scratch. We propose 2 techniques to tackle the challenges. The first technique is rule tuple compression. The core idea is to consider the tuples from the same rule in the dominant set as a virtual tuple. The second technique is prefix sharing, which reorders the tuples in the dominant sets so that more sharing can be explored when we compute the probability for different dominant sets. The empirical study shows that the probabilistic threshold top K query is useful in real applications, and the query evaluation algorithm is efficient. More details can be found in the following 2 papers. The implementation of algorithms, the synthetic data generator, and the real dataset used in the papers are downloadable using the following URL. Thank you for your attention.